Welcome back, pre-calcsters. I can feel the excitement in the air, even though we are separated by thousands of miles, because everybody has just been dying to do more with solving trig equations. So, as a quick reminder or review, just speaking it over, yesterday we saw at its most basic, when we solve trig equations, we solve it as though they're just single or multi-step equations that we saw in Algebra 1 or in 8th grade. And then we bumped it up and said, hey, if you take a square root, account for the plus or minus. If there's no interval, then we'll account for all infinity of our answers. If there is an interval, we'll pick it out. And then we looked at a couple examples of factoring stuff, which hopefully is starting to come back. It's been a little while since we did it. Today, we are still working through just solving trig equations. So this video, I suppose this lesson, is really and truly 5.3.2 or 5.3 all the same, and it's just solving, but we're looking at part 2. Okay, so yesterday the last examples that we did in class were of that quadratic type, where if you look back at your notes, what you'll recognize is that we had sine squared and sine, or cos squared and cos. Or on your homework, you might have had tan squared and tan. Now, in all of those situations, we had everything that matched. And what I mean by that is we could pick a u to substitute, and we could substitute it everywhere. When we jump in today, or right now when we are jumping in, because it's what we're doing like right this second, when we look at these, maybe that's not always going to be the case. So here we go. We are just continuing on. The last example in your notes should be from looking at quadratic type. The example today is when they're a little bit uglier. So maybe before we really deal with these as a quadratic type, maybe we need to rewrite it. And I'm going to pause this because this is looking a little bit blurry, and I think I know why, so I'm going to try to adjust something. And that looks a little bit better, but now it's going to look dumb when I write super large compared, but that's all right. Your notes don't have to change size. So when we talk about rewriting expressions, we're going to just jump right in by solving, and we're coming back to getting able to use and justify all the work that we did with the identities. So to jump in, let's just go ahead and start with 3 secant squared of phi minus 2 tan squared phi minus 4, but we're still just setting it equal to 0. Now, here we go. Right off the bat, if we like the technique, and I don't know, I can't tell right now if you guys have been doing it, if you like the idea of letting u equal something, this fails. Because if I make this u, this very clearly is not u anymore. Like, I can't even make secant u because these are different expressions. So we need a way around this. And the cool thing is we get 2 different choices. I can either replace secant squared via our Pythagorean identities with something with a tan squared in it, or vice versa. So replace one of these is really what we're after. And when I say replace, I do mean with a Pythagorean identity. Now, there's no right or wrong in this situation. I'm going to replace, for no particular reason, this tangent squared. So, unfortunately, I don't have a trig sheet in front of me, but check it out. We don't need one. If I want to get tangent squared, I'll divide everything by cosine, and I see tan squared plus 1 equals secant. Hey, which is really handy because there's a secant right here. And I guess it's secant squared rather, but same idea. So using this Pythagorean identity, I'm going to go ahead and replace this tangent squared with something else. So here we go. I would have 3 secant squared phi minus 2 times, and here's that magic, wonderful substitution occurring. Instead of tangent squared, I know that that is just secant squared phi in this case, minus 1 from my Pythagorean identity. So all I've done is replace this tan squared with this, and nothing else has changed. So the expression, depending on your point of view, it either looks nicer or it looks worse. I would advocate and argue that it looks nicer because I can deal with this without a ton of like additional thought. So all I'm going to do is clean this up via distribution. So I'll distribute here and here. So here we go. We get 3 secant squared phi minus a 2 secant squared phi when I distribute, plus 2 when I distribute, negative 2 times negative 1, minus 4, and it's still all equal to 0. Cool. Now, cleaning up a little bit further, I see 3 secant squared minus 2 secant squared. I think that's just a 1 secant squared phi. And then I see plus 2 and minus 4 looks like a minus 2, and that's equal to 0. Awesome. Once we get here, there's a couple different routes that we can take. Now, personally, I do not love dealing with secant squareds. So it's entirely up to you on how you want to carry through with this. I'm going to wind up changing this, guaranteed, out of secant squared and make it a cosine instead, because it's 1 over cosine. Now, how you do it and when you do it is entirely up to you. One option would be to add this wonderful 2, and I'll take the square root of this. So I get secant of phi is equal to positive or negative, really important, square root of 2, and I have it. Now, we don't normally recognize secants. So whether it happened up here or it's happening now, if we change this secant using our reciprocal identities, I know that 1 over cosecant of phi is equal to plus or minus root 2. And this is going to feel weird, but I'm going to do root 2 over 1 because the algebra or the simplifying, I'm going to take a different route than maybe we would normally think about. Rather than doing cross multiply and then dividing and having to rationalize, here's what I would rather do. I'm going to exponentiate, which remember just means this whole side gets raised to an exponent. I'm going to raise it to the power of negative 1, and I'm going to raise this whole side to the power of negative 1. Now, do not get this mixed up with the inverses. These are not inverses, these are reciprocals. Where that negative 1 lives dictates which one of those we're looking at. And it's terrible notation, but I didn't write it, so I don't know where you should file your grievance. However, when I do it to this side, and I flip the fraction, I wind up with just cosine of phi. When I flip this fraction, I get plus or minus 1 over root 2, but I'm not going to keep it 1 over root 2. I'm going to rationalize it so it looks like it should on the unit circle. And it winds up being root 2 over 2. So here we are all of a sudden looking at this expression, and all we're really asked to identify is where is cosine positive or negative root 2 over 2. And digging around our unit circle, I think that hopefully we can agree that it happens at pi fourths is the first place. Now, I haven't mentioned it yet, but we never specified an interval on which we were working. And if it's not specified, then there is no interval. It's just everything. So I'm going to go ahead and say, well, this is pi fourths, and I could do plus 2n pi, but I recognize that it's also going to be positive at 3 pi fourths and 5 pi fourths. Sorry, positive or negative at all the pi fourths on the unit circle. So based on a problem that we had done, I think yesterday, what I see is that pi fourths to 3 pi fourths to 5 pi fourths to 7 pi fourths, which is me just saying here to here to here to here, each of these is just a quarter circle away, or a pi half. And I'm just going to write this as plus n pi halves. Any number of half circles knocks this out. Cool. So time-wise, we're looking okay. If you guys need to pause it to discuss this idea, I am totally in favor of that because these rewritings are often strange and they aren't super comfortable until we get practice with it. Now would be a fantastic time to ask your neighbors. All right. If you need to pause me during, this statement, do so. If you guys are talking about it, I love it. If not, we're just going to continue on, and I want you working with your neighbors to do something similar for me. So I'm going to put a box there or a bullet to indicate my answer. So I want you guys to do the following, and there's not going to be any discussion. I'm just going to have the solution worked out as you guys are working it out, and then whoever pauses the video will resume it, and you'll see my answer. So here we go. I want you guys to do something similar to solve cotangent squared alpha plus cosecant squared alpha minus 7 and set it equal to 0. Now, you have options on what you replace. Here's the deal. Pick one to replace and stick with it. We may not pick the same one. Completely okay. Totally fine with me. Full disclosure, I would do cosecant because I know that that's going to turn into sine rather than an ugly fraction that we might get with cotangent, because I don't think about cotangents as comfortably. So go ahead, whoever is running the pause and resume, and pause it now, and you will see my detailed solution in 3, 2, 1, and here is my solution. Now, a little bit less work showing with it, and that's fairly natural, especially as you're working on your own. I'd take out the little steps with the algebra, and if you got to this first answer right here, I'm good with it. That's the good answer. This is our great answer for the same problem. Either these 4 or these 2 is the correct solution and would get full credit for our problems. All right. So we have a couple more examples to look at. We're going to keep kicking. It is hard enough when I have to read your facial expressions in class. It is super hard when I can't see your facial expressions because I'm recording this days in advance. So here we go. We have looked at how do we rewrite it to make it a quadratic type, which is exactly what we just did. Now there's one more technique that we're going to encounter that is super valuable and seems weird because I can't recall a time when we've had to do something like this before. But from time to time, we have to do some wonky stuff. And as long as we remember that whatever I do to one side of the equal sign, I do it to the other side as well, we're okay. So this example, we're going to call this squaring and converting. Now, it is unnatural to want to square both sides of an equation because it seems like all it does is make things more complicated. We can do it as long as we're consistent and we do it to both sides. We're not cheating. There's nothing that we have to worry about squaring that's going to break our function. The important part about this is the second that you wind up squaring stuff, you have to, or you must check for extraneous answers. Or extraneous solutions, rather. Those solutions that show up mathematically because of something we did, and it's squaring in this case, but when we squared it, we totally lost track of the negatives and things, and it happens. So we're going to work through one of these, and in that process, hopefully identify what it is that makes this problem, like why do we have to do it? So here we go. The first example is the following. I want to know when is it true that sine x plus 1 is equal to cosine x? And specifically, we're going to work on 0 to 2 pi. Okay, in problems like this, if you encounter a situation where it's really not clear what the first step should be, because I can't do anything to make sine turn into cosine off the top of my head. If I divide by cosine, I wind up getting a tangent and a secant, and it's just like things don't match. But that's okay. We're going to take this expression right here, and this is where we started. We're just going to take this, and we're going to square each side of this expression. So here we go. I'm going to use this orange color because I think I'm liking it more and more. I'm going to take this and square it, and I'm going to take this and square it. In the process, I am also going to make sure that I acknowledge the fact that I am not a freshman, and hence I don't freshman's dream, which means we actually have to distribute this out. So if you need to show the distribution, I encourage it. If you can do it in your head, I encourage it. As long as you're correct and you understand what's happening, I'm good with it. So when we FOIL this out, I wind up getting sine times sine, which spits out a sine squared. And then I'll show the work over here, sine x plus 1, sine x plus 1. So this is what it means to square something. And we're just going to distribute. Here's my sine squared, plus a sine x, plus another sine x. So it looks like plus 2 sine x. And then finally our plus 1. And allegedly that is equal to cosine squared x. Cool. Now we might have just found some nonsense answers, and we will deal with them. But notice what just occurred. I now have on the left side of this a nice quadratic where everything has the same variable, or sine squared and then sine. And then over here we have this pesky cosine, but now it's cos squared. And gosh, you know, I just have this gnawing feeling that maybe, just maybe, this cosine squared could be replaced via, I don't know, some Pythagorean identities into something that looks a little bit more fitting in with our problem. And verify this for me, but I'm pretty confident that it winds up being via our Pythagorean identities, and I don't know why this is doing that. I can't stop it and I can't erase it, so we're going to have to just live with that line in here. It's happened a couple times when it was paused. But nonetheless, Pythagorean identity, cos squared changes to 1 minus sine squared. So I'm going to rewrite this part of the line as well. Sine squared plus 2 sine x plus 1 now equals 1 minus sine squared. And I realize that I have one trig function through everything. Now, this is the hard part of the problem. I want you guys, now that we've seen this squaring technique, I want you guys to pause the video, and I want you to work through independently or with your neighbor, getting everything on one side, setting it equal to 0, and solving by factoring. Okay, I will have detailed work showing here in just a moment. Go ahead, pause it now, talk it out. I would begin by moving the 1 minus sine squared to the other side and solving it as normal, with the extra emphasis on saying, hey, check your answers afterward. And I'll meet up and I'll check answers with us, but I want you to pause this in 5, 4, 3, 2, 1. So we wound up getting a nice binomial where I GCF and I'm done. And here are the 3 possible solutions that we've come up with. We have 0, pi, and 3 pi halves. Now, to check these, I'm just going to go right back to the original problem right here. This is the one that we're going to check it with. So whether you do this in your head or if you physically write it down to check it, do not just blindly trust that they're going to be okay. I'm going to check each of these. If I take the sine of 0 plus 1, I need to check, is that indeed equal to the cosine of 0? So let's see here. The sine of 0 is 0 plus 1. And we're checking and seeing, well, is that really equal to 1? And, you know, I think it kind of looks like it is. So I'm good with this answer. 0 is good. I'm going to switch colors just so we can tell them apart a little easier, I hope. I don't know. I'm getting a terrible glare, so I'm having a real hard time telling them apart. Let's check pi. If I check the sine of pi plus 1, is it indeed equal to the cosine of pi? So let's see. The sine of pi is 0 plus 1. And I need to see, is that equal to the cosine of pi is negative 1. Now, if we say it a little slower, it's obvious if you thought yes initially. Is 1 equal to negative 1? And I think no. So check it out. This answer pi, garbage. Get it out of there. It's extraneous. The last one, if we check sine of 3 pi halves plus 1, I need to check, is this equal to the cosine of 3 pi halves? And let's check. Well, sine here is -1, plus 1 is 0. And is that equal to the cosine of 3 pi halves is 0? It is. We're good. So we conclude then in this problem, there are only 2 solutions, even though we found 3. Our 2 solutions here occur at the angle when x, or the angle x, when x is equal to 0, or when x is equal to 3 pi halves. Cool. If you run through these problems and don't check, normally I give you like full credit and stuff. If on a quiz, on a test, you do not check this and you just give me all 3 answers, I will take off way more points than I normally do for little mistakes. All right. So just like we've been doing here, I would encourage you guys, if you need an additional example or you want another example, go ahead, check out example 6 on page 368, and you will see another very similar, but another example done by your book. And if you guys really haven't read your book a ton, they do really well about annotating stuff. Cool. So we have been building this up. Today we took those quadratic types from yesterday and we saw that, hey, even if it's not a quadratic type, maybe I can make it one. Or if it looks nothing like a quadratic type, I can square stuff, and now I can make it look that way as long as I check for my extraneous answers. The last little piece, last thing that we're doing for new material this quarter is what happens when we have multiple angles. So we're going to look at solving multiple angles, or equations or functions with multiple angles. So I'll just say solving with multiple angles. Now, the language here, it is super easy to, not pay crazy careful attention to what's going on with this stuff, because so much of it feels definition-y or identity, and it is. But here's the big part that I'm going to sneak inside this example. If you consider something like sine of x, it's easy to overlook. But if I consider sine of theta, it's a little bit more natural. This is an angle. Specifically, it's an angle that's 1 theta. That's it. This is my angle. Now, if I contrast this with something that looks like sine equals 2 theta, I still see that theta is my angle, my argument of my sine function, whether it's theta or x, whatever, it doesn't matter. But what I see is that this is not 1 theta, but it's 2 theta in this situation. So I'm just going to have 2 different ones. I'm going to change that arrow. Instead of saying this is 2 theta, I'm going to say this is multiple theta. Now, the reason that I'm changing that language is because it doesn't matter if it's 2 theta or 1/2 theta, which is also a multiple of theta, or in the more general sense, we could look at this as some number k theta. In these situations, if this value of k, or b if we look at our old graphs and we just use letters to match up with how we simplify things generally, when we deal with this, we get the same techniques, but there's a little additional thought that's going to happen with it. So let's dig in and solving a multiple angle, which we'll get some identities out for some of these probably the day before we celebrate Pi Day. I don't know. Start thinking about the pies we're going to make after spring break. And let's jump right in. So here we go. Our first example is example A, and I want us to determine the value of t for which the following is true. I want to know when is it the case that 2 times the sine of 2t, and notice the specification or the argument with parentheses to be really clear, minus the square root of 3. I want to know when is that equal to 0. And looking at this, the problem, at least initially, doesn't seem that crazy. And I have a technique that I do. I think your book, if you're a fan of reading your book, I do it a little tiny bit differently than your book does. Or maybe not. I don't know. We'll see. Okay. So pretending that everything's the same, and it's just a regular angle in here instead of 2 times an angle, I'm going to do 2 steps in one. We can begin by isolating anything with the argument or with the variable in it. And I'm going to add a root 3 or a square root of 3, and I'm going to divide by 2. Now, in one line, that would produce the sine of 2t is equal to the root square root of 3 over 2. Okay. Nothing crazy has happened yet. Now, this is where the problems don't change, but we change the viewpoint just a little bit. I know that before, when we solved problems like this, we just had t. We write t equals this plus some amount of change. And it was always at 2n pi or n pi, whatever the case might have been. In this situation, I write this just a little tiny bit different. I know that 2t, my argument, 2t, and how do I want to word this? Let me rephrase this. I'm sorry. I know that there are places where my angle or the sine of an angle equals root 3 over 2. So I'm going to look at them and say, hey, all these arguments that are of the form 2t in this problem, where it spits out root 3 over 2, well, let's just think about where that happens. And again, if you need to for now, don't think of 2t, just think of x or theta, whatever it is. So I will, I'll cross it out and I'll rewrite it. If I don't know when is sine of x equal to root 3 over 2, I know that, well, that happens first. Sine is y, so I'm up at pi thirds plus 2n pi. Now, the other positive is going to happen at 2 pi thirds plus 2n pi. And this is just like the problems that we had done initially, a couple days ago. Now, when we cross it out, it feels a little bit more natural, but remember, the argument wasn't just x or t. It was 2t in this case. So I'm going to go ahead and replace that scribbled out mess back with 2t. And once we have this, and I have it all written out, I can solve for t. And to do so, I need to go from 2t on this line to just t. And I achieve this, and I'm going to show this here, by either dividing by 2, which is fine, or doing the same thing but making it much easier to think about, multiplying by 1/2. I obtain just a t on the left side of this equation. Now when I get back over to the right side, let's just see how this kind of sorts out. Looking at this thing, what we wind up getting when I distribute this 1/2 through all of it. Now I'm going to physically draw this in. 1/2 times pi thirds becomes pi 6. Now it's still a plus, but instead of 2 times 2n pi, I'm going to divide that in half. So it looks like plus n pi. And we have the first half of our answer. The second part, same idea, we're just going to distribute. 2 pi thirds times 1/2 becomes pi thirds. And just like we did before, when I distribute to the 2n pi, I get a plus 2n pi divided by 2 is just n pi. And we now have all infinitely many of our solutions for some double angle in this situation. And it wouldn't matter if we had a triple angle or a quadruple or a half, which love that I said it, because now seems like a pretty decent time to knock out a different value or a different multiple. So with your group, your neighbors, independently, as long as you're working, I'm good with it. I want you to solve the cotangent of x halves minus 1. And I want to know when is that equal to 0. And that's it. Sweet. So I will have whomever pause the video and let everybody work and resume once everybody's done. I will pause in 5, 4, 3, 2, 1. And here is my solution with a little bit of annotation to hopefully help out. Now, I'll give you a moment to look over this, and it might be awkward silence, but that's all right. Let's check, let's compare, and I'm going to start talking in like 15 seconds. So, when we look at this, couple things that I do want to expand on, and I've been trying to avoid doing this after you guys do a problem, because if you're all getting through it well, then this is for nothing. But in the case that somebody struggles with this line here to here, I am trying to skip as much math as I can. And I'm going to sneak in the middle steps here that if I don't just use this exponentiate where I raise both sides to -1 or I cross multiply, I want to make sure we can see where that work happens. So I will pick back up, and you don't have to erase anything, but if I have our first step where we have cotangent of x over 2 equals 1, then in my next line, I think that I can determine pretty confidently that 1 over the tangent of x halves is equal to 1. And now I just cross multiply. So maybe it's not a huge deal in this situation, but oftentimes it will be. I'll multiply both sides by tangent of x halves, and we get to where we left off. So the other part of this problem, though, where I was maybe concerned or that I can foresee some issues happening, is I know that tangent is 1 at pi-4ths in quadrant 1, and it's also positive 1, because that's what we had, at 5 pi-4ths. And these are exactly half a circle apart. Now, this answer is okay, but if we look back and recall that tangent has a period of pi instead of 2 pi, then these are really the same answer. Like, I get the same one over and over. So I can simplify this expression in this, because that's my period, and then we do the same thing. I know that if this is what the argument has to be, or my angle, but it was x over 2 instead of just x, I'll just multiply both sides by 2, and we're done. Okay. This stuff takes practice, like everything in life. Please don't hesitate to email me if there's questions, concerns. I welcome the chance to do a little bit more math in my spare time. Not even faking, like not exaggerating. However, if you do email me, I am not taking my textbook with me on my trip. So please, if you email me, either do so with a picture. Yeah, well, just that. Either a picture or you type the problem out so I can see what it is. But I want you guys to have the remainder of class to continue working on homework 5.3, which if I look here, it's somewhere over here. 5.3, this guy. You should now have the capability to do 39 through 47 odd, 63, and 85 through 87 for all of the assignments this week. I know it's crunch time, it's the end of the quarter. If you have maybe neglected staying up to speed with all of your, trig stuff, you have until Friday night at 11:59 p.m. So as late as possible on Friday to get all these turned in. Remember, they are pictures of your work submitted to Google Classroom. Tomorrow in class, you guys will be working the Chapter 5 review. In prior years, this was a quiz, but it didn't feel right giving you a quiz when I wasn't there for, a ton of this chapter. So, bring me back, get your homework turned in tomorrow, bring me back your review thing on Monday following spring break. Tomorrow in class, I would encourage, as always, work as much of it as you can without ever opening your notebook. I don't mind if you guys are collaborating and working together so long as it's actually working together and not just one person working and one copying. Cool. Hopefully this was helpful, and I will see you guys Monday after spring break, and maybe sooner, depending if people email me with questions and such. So I will see you then. Everybody have a wonderful spring break. Don't go crazy doing too much math. I know you will, whether I say it or not. All right. See you guys after the break.